Hello, so today we will still be doing exercises about velocities and accelerations. If you remember, we had discussed something about radial and transverse directions, tangential and normal directions. According to the formula above and according to the formula below, we will have to use. Always remember that radial and transverse directions will only be used for polar coordinates, whereas over here it will be used for intrinsic coordinates. Okay, so let's see. Okay, so we will solve example 1.6, example exercise 1 and exercise 2. Okay, so let us start things with example 1.6. If you are reading the question, the velocities of particle along and perpendicular to the radius vector are lambda r and mu theta. So you can immediately see that it is a question involving radial and transverse direction. So we will be employing the formula above. Okay, so let's see. Okay, let me just minimize this. Okay, so the velocities of a particle along and perpendicular to the radius vector. Okay, so we are having the solution for example 1.6. Okay, the velocity along the radius vector, that is r dot. Okay, and if you remember, r dot, it is dr dt, theta dot, it is d theta dt. Okay, keep that in mind. Okay, so along the radius vector, it is r dot, and it's given by lambda r. Okay, maybe I will use the same letter. Okay, r dot is lambda r, and the velocity perpendicular to the radius vector, that is the transverse velocity, it is r theta dot. R theta dot, it's given to be mu theta. Okay, so if you are taking a look at the question again, we have to find the path, and also we have to show that the accelerations along and perpendicular to the radius vector, okay, are according to those equations. Okay, so first of all, we have to find the path. Remember that if you have to find a path, it should be an equation that is independent of time. Time should not be involved. Over here, if you are taking a look at this equation, okay, let us name this one as equation 1 and this one as equation 2. This one still has time in it, because over here r dot, it is dr dt. Okay, it still has time, so that's why, okay, it's not the required path. So this is what we get. Okay, theta dot, it is d theta dt. Okay, so we have to eliminate the time, so we can divide this equation by this equation. Okay, dividing, okay, maybe 3 and 4. Okay, let's see, dividing 4 by 3, dividing 4 by 3. Now let me just minimize this question, you will need it again. Okay, so if we divide it, we will be having r d theta upon dr, it's equal to mu theta by lambda r. Okay, so once you reach this stage, now you just have to separate the variables and integrate. Okay, we'll keep theta to this side, theta upon theta, dr upon r, mu by lambda. Mu and lambda, they are constants. Okay, so you can keep them anywhere. Okay, so now we just have to integrate. Let's see. If we integrate, what are we getting? We are getting log theta, mu upon lambda, dr upon r. Okay, just let me read the question again. Okay, all right. Okay, so actually over here it will be, okay, so it will be r squared. Okay, so over here I made a mistake, it should be r squared. Again, take a look, r and r, okay, will give you r squared. So over here, if you integrate, this one will be minus 1 upon r plus a constant. Okay, the constant, you can keep it as c, or since we are having log over here, we can keep it as log c. Okay, so what we will do, we will transfer this log to this side. We will be getting log theta minus log c, mu upon lambda. Okay, this is what we will be getting. Okay, so after doing this, Okay, now we can just use properties of logarithms. Okay, we will be having log theta minus log c will give you theta upon c, e power minus mu upon lambda r. So theta will ultimately be equal to c e power minus mu upon lambda r. So this is the required part. It is a required part because it no longer contains time. Okay, sometimes we can even involve time. Okay, but for this question, okay, since we can easily eliminate time by doing all these steps, this one will be the required part. Okay, also I will be needing these equations, which is equation 1. Okay, so I'll keep it to this side, and also r theta dot equal, okay, how much was it given again? R theta dot equal mu theta. Okay, so now if you take a look again at the question, we have to show that the radius, that the accelerations along and perpendicular to the radius vector. So let's try. So that means we have to find the radial acceleration and the transverse acceleration. Okay, this one is equation 2. Now, radial acceleration, it is given by the formula above, which is equal to r theta double dot minus r theta dot square. So r, okay, r double dot, it can be written as d dt r dot. Okay, so if you differentiate something with an r dot, you will get an extra dot, which is r double dot. Okay, so over here we can write it as d dt r dot minus r theta dot square. So this is what we are given. Okay, d dt r dot, but r dot it's lambda r. So we will be having d dt lambda r minus r theta dot square. Theta dot square, according to this formula, according to equation 2, you will be having mu theta upon r holding square. Okay, using 1 and 2. Using equation 1 and equation 2, you will be having this. Lambda, it is a constant. Lambda, it is a constant. You can take it outside. dr dt. So you will be having r dot. Okay, again, lambda, it is a constant. dr dt will give you r dot. So this one will be, we will be having r with r square 1 by r mu square theta square. Okay, so lambda, again r dot, it is lambda r minus mu square theta square 1 r. So ultimately we will be having lambda square r minus mu square theta square 1 r. Okay, so let us just see whether that is the required expression or not. Okay, so as you can see, it is indeed the required expression that we want to find for the radial acceleration. Okay, so now let us find the transverse acceleration. Okay, transverse acceleration, according to the formula above, it is 1 upon r d dt r square theta dot. So what we can do over here is, okay, we can use the product rule for this one, but actually we can simplify first by using equation 2. Okay, this one can be written as r theta dot r theta dot, it is mu theta. So r mu theta. So over here we will take mu, which is constant, we can take it outside, mu upon r d dt r theta. Okay, so now that we have reached this stage, what we can do, we can apply the product rule. Okay, mu upon r. Over here we will apply the product rule for derivatives. d theta dt plus theta dr dt. So this is what we will be having. So we will be having mu by r theta dot plus theta r dot. So now again we can substitute theta dot from this first equation. Okay, we will be having mu by r theta dot, it is mu theta according to equation 2, theta r dot, so we'll give you theta lambda r, again using 1 and 2. So this is what we are having. So now we just need to simplify it. Okay, we will be having, okay, theta you can take it outside, it is common in both, mu plus lambda r. Okay, let us see whether that is the required expression or not. Okay, you actually just have to keep, okay, you just have to simplify it to obtain something as in the given expression, which we can easily do. Okay, so you need to keep only mu and theta outside. So this is what we are having. Okay, r you can multiply it again inside, we will get mu by r and lambda. Okay, so this solves the first question. Okay, so now let us try to do question number 2. Okay, that was example 1.6. Now let us try example 1. Now exercise 1, if you are saying a particle moves along a circle r equal to a cos theta. Again, it is a question involving the radial and transverse directions. That's why we will be using the formula above. Okay, acceleration towards the origin is always 0. Okay, so let's try to interpret that. Towards the origin is 0. Okay, the origin can be treated as the pole. Okay, so that is why the radial acceleration, it will be 0. If you are not seeing the formula above, the radial acceleration, it is r theta dot minus r theta dot square. Sorry, it's always 0. Okay, so this is what we are having. Okay, we need to find d2 theta. Okay, I will just write over here, we need to find d2 theta dt square. Okay, so let's see. Okay, so over here we are having r double dot minus r theta dot square. So let's see. Okay, this one will be equation 1. And the first equation it is r. Now this is the part, r equal to a cos theta, which is the part. Okay, so what we will do, because over here we have r double dot minus r theta dot square. So we will have to differentiate this one with respect to time. Okay, differentiate with respect to time, we will be having this 2a, it is a constant, so we will be having d dt cos theta. Again, I'm writing it step by step. Once you are familiar, you can easily skip some steps. dr dt, this r naught 2a, d dt cos theta will give you minus sine theta d theta dt. Okay, so this is what we are having. But d theta dt, it can be simply written as theta dot. Okay, so we can easily skip that step. We can write it as simply as theta dot. Okay, or r dot equal minus 2a sine theta dot. Okay, again we will be needing another dot, so that's why we will again differentiate it with respect to time. Okay, minus 2a d dt sine theta dot. Okay, we will keep this equation. Okay, maybe we will need it, maybe we will need it or maybe not, but let us just keep all the equations that we have 2 and this one as 3. Okay, so now let us differentiate this one. d dt r dot will give you r double dot minus 2a. Again, for the right hand side, for the right hand side, we will have to use the product rule for differentiating this one. So we will be having sine theta ddt theta dot will give you theta double dot plus theta dot ddt sine theta will give you cos theta dot. Okay, so let me just write over here, okay, in case you were wondering. Ddt sine theta, it is cos theta d theta dt. Okay, so that's why we will be getting cos theta dot. That is exactly what we are having here. So ultimately we are getting r double dot equal minus 2a sine theta double dot minus 2a theta dot square cos theta dot will give you theta dot square. Okay, so let us just name this one as equation 4. Maybe we will need it. Okay, so now what we will do, since we have found out r double dot, we can substitute all these in the equation 4. Okay, substituting in equation 1, let us see what we will get. Okay, I'll write here, substituting in that equation. Okay, which is minus 2a sine theta double dot minus 2a theta dot square cos theta r double dot minus r which is 2a cos theta dot square. Okay, I'll just write it as theta dot square. Okay, so this is what we are having, and all of this, it's equal to 0. Again, this one is r double dot minus r theta dot square. Okay, it's equal to 0 if we substitute it in equation 1. Minus sign, this one is a minus sign, but it's okay. I hope that is clear. It is minus sign. Okay, so now what we can do, we can cancel all the 2a, so we will be having minus sine theta double dot minus theta dot square cos theta minus cos theta dot square equal to 0. So what we will be having, okay, if you are noticing, this one and this one, they are exactly the same, so we can write it as minus 2 theta dot square cos theta. So we can take this one to this side. We will be having theta double dot equal minus 2 theta dot square cos theta upon sine theta. So I think this is the required expression. Let us just see. Okay, yes it is. So we can easily write this one as 2 theta dot square cos theta by sine theta, which is cot theta. Okay, so this is the required expression for theta double dot. Okay, that we want to find. Okay, so this is again a very exercise, okay, which we are done. Okay, so now let us try the last exercise for this video. So sorry. Let us try the last exercise for this video. Okay, a point moves in a plane so that its tangential acceleration is constant. So if you are not seeing the question, we have to use the formula below. The tangential acceleration is constant. Okay, so let us just write it down. Solution for number 2. Tangential acceleration is constant, so we can write ds dt equal k. Okay, let's denote it with k, which is constant. Okay, and also the magnitude of tangential velocity and normal acceleration are in a constant ratio. Magnitude of tangential velocity divided by normal acceleration. Okay, it is equal to another constant. Okay, maybe. Okay, let us just use some Greek letters. Okay, lambda and mu. Okay, let's see. Okay, now we have to show that the equation of the path. Okay, so the equation of the path, again, it won't involve time. Okay, so this is all the information that we have. We have to find the equation of the path. Okay, so okay, just let me see again. Okay, actually it's given that the tangential acceleration is constant, so d2s dt squared. Okay, I made a mistake. Okay, so what can we do? Over here, this one we can easily write it as d2s dt squared. If you are not seeing the formula below, we can write it as d dt ds dt equal lambda. Okay, and over here for this equation, tangential velocity, which is v, normal acceleration, v squared by rho, is equal to mu. Okay, they are all constants. For this one, we just have to separate the variables and integrate. Okay, so over here ds dt equal lambda dt. Okay, so now we can integrate it. I'm taking this dt to this side, I'm getting lambda dt, so we can integrate. Lambda is a constant, we can keep it outside. So over here we'll be having ds dt equal lambda t, okay, plus another constant. Let us name this constant maybe c1. Okay, so this is what we are having. Okay, some of you may be thinking, how did I get this? Okay, just remember, integration dz, how much will it give you? Z, right? Integration dz, it gives you z. So similarly over here, integration of d, take this one as z, it will give you z. Okay, so again we can separate the variables. ds lambda t plus c1 dt. Again we can integrate. Integration ds will give you s. Integration of this one will give you lambda t squared upon 2 plus c1t, okay, plus another constant c2. So this is what we are having from this first equation. Okay, now let us try this one. For this side, we will be having rho upon v equal mu. But rho, if you take a look at the formula below, rho it's given as ds d psi. And v, again if you take a look at the formula below, it is given as ds dt equal to mu. Okay, so we can do this. We can write dt on d psi equal to mu. Okay, we can separate the variables. We can write it like that. dt upon d psi equal to mu. Separate the variables. Mu d psi. Integrate. Integrate, you will be getting t equal mu psi plus c3. Okay, I've already used c1 and c2, so over here I'm using c3. Okay, just name this one as equation 1 and this one as equation 2. If you take a look at the question, s should be on the left hand side and psi should be on the right hand side. And again, the equation that we want to find should not involve time. So that is why we can substitute equation 2 in equation 1 to get the required answer. Okay, substituting 2 in 1. Substituting equation 2 in equation 1. We will be getting s equal lambda upon 2. T square, you can write it as mu psi plus c3 whole thing square plus c1 t, again you can write that as mu psi plus c3 plus c2. Okay, if you simplify this one, these are all constants. Okay, Again, if you expand this one by using the formula, you will be getting a term containing chi square, right? You will be getting a term containing chi square. You will also be getting a term containing chi, and you will be getting a constant. So ultimately, similarly over here, we are having a term containing chi. We can add the term containing chi from over here and the term containing chi over here. We can simply write this one as a chi square plus b chi plus c, okay, which is the required expression, okay, where a, b, and c are constants. Okay, if you are not comfortable with writing this one directly like this, you can just expand. You can just expand this one and then group the terms containing chi square together, group the terms containing chi together, and group the constant terms together. Okay, you will be getting this. Until next time.